Okay, everything that we know about electrons comes from the study of light. And if you know anything about electrons and light, it kind of has this dual nature about it where it can behave both as a wave and as a particle. So we kind of need to study and go over the components of waves. The length of a wave is from crest to crest or from trough to trough, and we call that the wavelength. Notice that this one right here has a longer wavelength than this one right here. This has a short wavelength. Frequency, the longer the wavelength, the smaller the frequency. The smaller the wavelength, the larger the frequency. So they're inversely proportional here. The number of times a wave repeats itself per second. What I always like to say is if this was ocean waves, how often would they hit the shore? This is going to hit very often, so it's got a high frequency. This one's not so much. The larger the wavelength, the less frequently it hits. So we've got c equals lambda nu. C stands for the speed of light, which is 3 times 10 to the 8 meters per second. I'll always give you that. Lambda is going to be wavelength, which is going to be measured in meters because this is in meters right here. Unfortunately, I'm probably going to be giving you the wavelength in nanometers, so you're going to have to convert that. Nu is frequency, which is measured in per seconds, or what we like to call hertz. So for example, find the frequency of a green light that has a wavelength of 545 nanometers. There's that nanometers. Nano just means times 10 to the negative 9th. So if I plug in everything that I have right here, I have the speed of light, 3 times 10 to the 8th. Then I'm just going to plug in 545 times 10 to the negative 9th meters. That gets me an answer of 5.50 times 10 to the 14th hertz. This is the continuous spectrum of light that we can see. Okay, this is all electromagnetic radiation, but we can only see this little section right here. We've got our Roy G. Biv, if you will. If I go beyond this section right here, that's going to be called ultraviolet. If I go past this section right here, it's going to be called infrared. Notice once again that red has the largest wavelength, big red. Blue and violet over here has the lowest wavelength, and remember, the lower the wavelength, the higher the frequency. The higher the wavelength, the lower the frequency. This is called spectroscopy. If I take white light and I bend it through a prism, it's going to produce some sort of spectrum. Okay? This one in particular I can tell is hydrogen. Hydrogen emission looks like this. Every time you look at a hydrogen emission, I get this kind of a violet color, indigo, blue, and then kind of a yellowish orangish color. Okay? This is the fingerprint, if you will, for hydrogen. Hydrogen is the only one that emits this spectrum. Why do we have different colors? Because as wavelength and frequency changes, the color changes. There's that dual nature once again. Light can behave as a wave. It can also behave as a particle that we like to call a photon. As wavelength and frequency changes, the energy per photon changes, and that brings us to the concept of energy. Energy for light energy, is equal to Planck's constant times frequency. So basically, this one is going to be a direct relationship. The higher the frequency, the higher the energy. So if you ever solve for frequency, all you have to do then is multiply it by Planck's constant, 6.63 times 10 to the negative 34th, and you'll get the energy per photon, and that will be in joules. So when sodium is excited, it emits yellow light with a wavelength of 589.0 nanometers. Find the energy per photon of this light. So what I'm going to do is I'm going to take my wavelength and the speed of light, solve for frequency. Once I solve for that frequency, I'm just going to multiply it by Planck's constant to get the energy. So the first thing I'm going to do is take my speed of light, divide it by the wavelength. That's going to get me frequency. Take that frequency, multiply it by Planck's constant. That gets me energy, 3.38 times 10 to the negative 19th joules for every one photon. Okay. Why do atoms produce atomic light spectrums and multiple colors? Well, there's so many choices that can happen here. Let's see, like an electron that's in the first energy level jumps from the first energy level to the second energy level. Well, it takes a certain amount of energy to go from here to here, and it doesn't stay there long. It jumps back down. When it jumps back down, it's going to release a certain amount of energy. Okay? Oops, I'm looking at the wrong one. Here's the one from first energy level to second energy level. It doesn't take that much energy to go from the first energy level to the second energy level, so that low amount of energy is going to result in a low frequency, which is then in turn going to result in a large wavelength. This one right here is going from the second energy level, the third energy level, down to the first energy level. So that's a little bit larger amount of energy. The larger amount of energy is the larger frequency. Larger frequency results in smaller wavelength. This one's jumping from the fourth energy level all the way down to the first energy level. That's a large change in energy. The large change in energy equals large frequency. Large frequency equals smaller wavelengths. Okay? Remember, when an electron is in its ground state, it's in its normal state. Okay? If I excite this electron, if I set it on fire, if I run electricity through it, it can jump to a higher energy level. When it jumps to that higher energy level, this is called the excited state. So we've got the excited state and the ground state. The Heisenberg uncertainty principle says that it is impossible to know the exact position and momentum of an electron at any one instant in time. So this kind of gets us to the quantum model of what an atom actually looks like, this big cloud of electrons. There's 4 quantum numbers that you guys need to be familiar with. They are the n, the l, the m, sometimes called the m sub l, and the m sub s. The n number is called the principal quantum number. That's going to tell you the energy level. The L is the angular momentum quantum number. Sometimes they call that the azimuthal number. That's going to tell you the sublevel. The M sub L is going to be the magnetic quantum number. That's going to tell you which orbital it's in. And then the ebb sub S is the electronic spin. Is it spinning clockwise or counterclockwise? Okay? So the principal quantum number, N, is which energy level? The lowest energy, higher energy, and then continuing on in higher energy. This energy level is sometimes referred to as a shell. The angular momentum number, or the azimuthal number, or the L number, is going to tell you what sublevel it's in. Is it in the S? Is it in the P? Is it in the D? Or the F? SPIDF. Okay, we're going to call the S 0, the P 1, the D 2, and the F the third. One thing that they always say is the angular momentum number, it can be any quantum number, n, may contain sublevels of 0 all the way up to n minus L. So for example, if you have the third energy level, then you can have sublevels of 0, 1, and 2. The magnetic number is going to be some sort of number between negative L all the way to positive L. So if it's negative 1, 0, or positive 1. This is what the s orbital looks like. It's kind of spherical. This is what the p sublevel looks like. Looks like kind of a figure 8. Okay. Now this is the p in the x-axis. This is the p in the y-axis. If I lie this one down towards you, that would be the p in the z-axis, which is right here. You're kind of looking at it. Okay. So these are the 3 p's: the x, the y, and the z. Don't forget, electronic spin is when one of the electrons is spinning clockwise, the other one's going to be spinning counterclockwise. So we're going to give it a positive 1/2 for clockwise and a negative 1/2 for counterclockwise. We're going to practice this in class. Finally, the Pauli exclusion principle says it is not possible for 2 electrons in an atom to have the same 4 quantum numbers. There's 3 rules that go with this. The Aufbau principle, which says that electrons like to enter orbitals of lowest energy first. Pauli exclusion principle says that you only have 2 electrons per orbital. And then Hund's rule, if you'll remember, says you put 1 in each orbital before you double up.